Quality of Service Part 2, Congestion Management and Avoidance. Well, welcome to the second part in the trilogy of Quality of Service. In the last nugget, we looked at how we can classify our traffic and mark it so it's seen in certain ways, either using the IP precedence or DSCP value throughout our entire routed network. So all the routers can see how you've classified and marked your different traffic. Now we're going to tell our router how to juggle that traffic, because it's going to be receiving these traffics that are marked with certain markings, and we need to tell it how do you treat those. If you leave off with the first part in the Quality of Service series, nothing different happens. All the packets flow around marked, but nobody knows what to do with them. So we're going to start off here talking about the legacy queuing methods. And you might think, well, Jeremy, why are we talking about the old way of doing things? Well, the reason why is there's four major methods that used to be around and are still around in quality of service. They are FIFO, priority queuing, custom queuing, and weighted fair queuing. Some of you might have heard of some of those before. The modern queuing methods, which include class-based weighted fair queuing and low latency queuing, are nothing more but hybrids of the legacy queues. So by understanding the legacy queues, you really are finding the building blocks that you're going to use to understand the modern queuing methods, and it will really help you understand how to deploy them and what the strategies you should use are. From there, we'll get into managing congestion using weighted random early detection. This is a really neat feature, really easy to enable on your router. I don't know nowadays why it's almost not done by default, because by default your router is just going to drop everything once its queues are filled up. That's known as tail drop. We're going to look at how to make the router do it a little better way so it can selectively drop packets that maybe you don't care as much about. Well, let's start things off by talking about the legacy queuing methods, and these are still available and still in use in many networks on Cisco routers. These are the queuing methods that you would deploy using the CLI, the command line interface, before the modular quality of service, the MQC standards, came about. Now, I'm sure you're looking at these pictures going, what is this all about? Trust me, I'll get into that. Let's start off with what the legacy queuing methods are all about. The typical queuing method that is on by default on every router is first in, first out. And you know what? Before I even talk about these, queuing methods are only implemented when there's congestion on your router. That's why they call these queuing methods congestion management. So I'm going to go through all these queuing methods, but remember, if your router isn't congested, as in it's got enough bandwidth to send everything without having to put things in memory buffers and queue it up, these methods are not used in that case. So queuing methods are implemented once the router has so much traffic that needs to leave. Maybe you got a T1 line as a bottleneck. So much traffic's backing up that it has to start queuing them up in its memory buffers. Okay. FIFO. It works just like the good old cattle call at Disneyland. And I've got to admit, I'm one of those people that I don't like lines. Standing in lines just drives me nuts. And I'd be this guy standing at the back looking up at the sky going, oh, will this line ever move? That's your voice packet in a first in, first out type network. It's the one that first in, first out queuing works in the sense that if you get there first, you're going to get out first. It just queues it up in order, and that's logical. That's how it does it by default. Now, if you decide to go with priority queuing, well, priority queuing works like if you were buying a lawnmower. Well, not just one lawnmower. How about lawnmowers for your whole family and the whole neighborhood while you're at it? Let's say that there's 3 stores, and let me grab my right pen here. There's 3 stores that are selling lawnmowers, and these stores, you know, I'm just gonna pick some names, but they may or may not have lawnmowers on sale. We'll say Walmart is selling them, Target is selling them, and Radio Shack got some in special delivery. They're selling some lawnmowers too. And Walmart, you know, watch for falling prices. They're selling lawnmowers for $1 a mower. Sale of the century. Target is selling lawnmowers for $10 a mower. And Radio Shack, well, they had to special order them in, so they're selling them for $100 a mower. Now, if you were buying lawnmowers for your whole family and the neighborhood, where would you go first? Well, logic dictates, go to Walmart. You would buy what at Walmart? You would buy all of the lawnmowers that they had. Clear off the shelves. Make sure that every single one. You would never go to Target unless Walmart was completely empty. So once Walmart ran out and you still had more lawnmower to buy, you would go ahead and you would hop over to Target and you would buy that one lawnmower. Now, My guess is that if you're like me, you're a budget shopper. After buying that one lawnmower, you're thinking, man, you know what? I'm going to drive back to Walmart and check and make sure they don't have more in stock. Check there. Oh, none in stock. Okay, I'm going to go back to Target. That same system's going to follow along until you clean Target out. And pretty much the only time you'd buy a lawnmower from Radio Shack in this case is if both Walmart and Target were completely out of lawnmowers. That is priority queuing. But instead of lawnmowers, you have traffic types. You get to dictate what traffic type ends up at each store, and your router will service them in a first store sort of basis. I'm trying to equate this analogy. Here's the idea. We're going to have a high, medium, normal, and low priority queue. There's actually 4 stores in that case. Whatever packets we dictate to go into the high priority queue, well, that's going to get serviced first. And if there's always packets in that queue, guess what happens to the medium, normal, and low queues? Well, you got it. They never get answered. That's why priority queuing is often called brutal queuing, because all of these other queues, if there's a lot of high priority and even medium priority traffic, the lower priority queues never get serviced. So we had to find a better way. Welcome to custom queuing. Custom queuing is like a Krispy Kreme donut. Actually, a lot of Krispy Kreme donuts. Now, I don't know if you have a Krispy Kreme donut shop by you. We just got them here in Arizona not too long ago, but they are spectacular. They have these donuts that just come steaming off the rollers, and you pick them up and they literally melt in your hands. They are fantastic. So when I go to Krispy Kreme donut, I stand up in the line and I say, you know what, I'm going to have 12 glazed donuts, maybe 6 of those, the pink donuts with the pink frosting on it, 3 of the chocolate donuts, and just 1 of those filled donuts. You never know what that filling is. So I'm just gonna take that as my order, and I take it back. You can actually dine in at Krispy Kreme. You sit down at the table. I take those donuts back to my table and I gobble them up. Chomp, 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 chomp. I then think, more donuts would be good. And I go back up to the counter and I get exactly the same number: 12 glazed, 6 pink ones, 3 chocolates, and a odd cream-filled donut. Go back and eat them all up. That is how custom queuing works on your Cisco router, but now instead of donuts, you have packets. You have HTTP packets, FTP packets, maybe POP3 packets, and then finally the lowly telnet packet. The idea of custom queuing is that the router will service your queues in a round-robin fashion. Not as brutal as priority queuing, but yet giving some of these packets a slight priority edge, such as HTTP. For every round that it goes around, you'll have 12 packets sent, or it's actually dealt with in bytes. So 12 bytes of HTTP for every 6 bytes of FTP, for every 3 bytes of POP3, for every 1 byte of telnet. Round and round it goes. And that's how you can give some the advantage, but not starve out the other ones completely. Finally, weighted fair queuing is like a meeting. Meetings, I'm sure you've been to many of them yourself. They're not my favorite things in the world, because believe it or not, in a meeting, I'm typically this guy. The guy in the lower right-hand corner. Believe it or not, on personality test scales, I score extremely far on the introvert side. I know, it's kind of odd, but I am very quiet, very reserved. I don't talk too much outside of talking about Cisco. But in this meeting room, you've been to a meeting, there's always the 1 or 2 people. Maybe you're one of those people. I'm not talking down to those people, but there's the 1 or 2 people that always have something to say about everything. The new topic gets brought up. This person stands up over here and talks about the topic. And then someone has a comment, and they have to chime in. Let's talk about that comment. Well, one thing I noticed is at the meeting, did you ever notice how that person who's talking, they kind of don't have as much priority as that person who doesn't say much? I mean, if they talk, they get heard. Sure, people listen to them, but not as much as if the guy who never says a word stands up and says, I have something to say. You ever notice what happens? Everybody's like, oh, it's the quiet guy. What's he going to say? Because everybody's kind of curious. They've heard this guy talking for so long, they want to hear something different. That is weighted fair queuing on your router. The router will take the high volume senders and receivers that are sending a lot of traffic. Maybe you have a FTP session going, blah, 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 blah. It's talking on, eating up the bandwidth, and all of a sudden, a low bandwidth sender comes in, maybe Telnet. Telnet sends, one packet at a time, one character at a time as it sends. So when it comes up, it says, excuse me, I have an A. And the router says, oh, wow, you never said much. I'm going to prioritize you above the high volume sender. So weighted fair queuing, I always like the name because I think of it, it's just fair. The people that are talking a lot, they don't get the priority, whereas the people that are talking a little get all the priority. As I mentioned at the beginning of this nugget, the reason I talked about the legacy queuing methods, which are still in use widely across many networks in America and around the world, the reason I talk about those is because the modern queuing methods are nothing but compilations of multiple legacy methods. Somebody looked at the custom queuing, which every time I say it, I think of custard queuing with my donut analogy. Custom queuing allows you to have up to 16 different classes of traffic, and you can say how many bytes are serviced from each queue of traffic. So I could have, HTTP being one and FTP being another. But you know what? Eventually, you're going to run out of classes. With 16 classes, you can have 16 different traffic types, or 16 different applications, I should say, and you'll end up compiling some of them. You might say, well, HTTP and maybe I'll just put HTTPS, and I'll throw FTP, all go into Q1. And for Q1, I say, for each go around, I'm going to take 2,000 bytes of data. So you kind of run out of queues with that class-based system. So somebody said, well, it would be awesome if we could combine custom queuing, which is our donut method, with weighted fair queuing, which says the low volume senders get priority over the high within that queue. So maybe we have HTTP, HTTPS, and FTP all going in the same queue. Well, we're going to service 2,000 bytes from that queue, and you know what? Within there, I'm going to take maybe HTTP because it's the lowest volume sender out of the three. So when you look at this, it's just combining multiple ones together. The most common way of implementing this is you'll end up with your different classes, your different groups that you've assigned, and then the default queue, which is pretty much anything that is not classified, that you say, you know what, that's not important to me, I have a default group, that will end up being weighted fair queued. So you'll have your custom queuing for most traffic, and then you'll have your default queue, which is everything left over, that gets weighted fair queuing. Now, the nice thing about this method is it gives you flexibility, but it's still missing something. And that's the ability to give priority. Now you might say, well, wait a sec. You can give priority because you could say, let's say we have our voice queue. You had voice over IP, and that goes in queue number 1. And then 2, 3, 4, you have all these other queues that have different data types. You could say, I want to service a lot from this voice queue, whereas these other queues, don't get as much. So I'm giving priority, right? Yeah, but you're not giving the kind of priority that voice needs. Voice has very, very specific delay requirements. It has to get from point A to point B in 150 milliseconds or less, and that's a pretty tight requirement. And here's the problem with class-based weighted fair queuing. Voice queue, you may get a bunch of service, but as soon as you reach that byte limit, guess what happens? Chunk, you shift down to this queue. Voice starts piling up. Chunk, shift down to that queue. Voice is piling up. Chunk, we go down to that queue. You see, it's kind of going down here. Meanwhile, voice, the delay is just going through the roof because we're waiting to loop back around to that voice queue. We need to give voice the ultimate priority. That's where low latency queuing, a moment of silence. Low latency queuing adds nearly all the queuing methods together. You have your weighted fair queuing that you can have for the default queue, and most traffic is going to be put into the classes that you get to say how much bandwidth is serviced from each one of those classes. But then you have the sacred priority queue. Remember the lawnmower queue. Where are you always going to go to get the lawnmower? The place that sells it for $1. Same thing here. You get to define one and only one priority queue that you're going to define for low latency queuing. That priority queue might be voice, might be video, whatever the extreme sensitive traffic is, gets service first, no matter what. So you might be going in your round robin, life is good, you're going in your circles, and all of a sudden a voice packet comes into that priority queue. Everything stops. It says, you know what, no more donuts for me, I'm grabbing that voice packet and I'm sending it because that is my priority traffic and I get to it first. And you might be thinking, well, wait a sec. Didn't priority queuing have the inherent problem that if there was too much high priority traffic, nothing else would get serviced? Yes, it did. And the creators of low latency queuing thought of that and implemented something called policing, which we're going to talk about in the third quality of service nugget, but I'll mention it here. They've implemented policing on that priority queue. Here's what that means. You as the administrator get to specify how much bandwidth that priority queue can consume. We'll say 300 kilobits per second, right? So what it will do is it will service 300 kilobits per second of that priority queue, maybe voice, maybe video, whatever the case may be. And as soon as you reach that number, you're cut off. That's it. Chop. You don't get any more priority bandwidth until the next time interval. So what that means is you as the administrator need to make sure that you don't oversubscribe that queue, because it's going to get cut off so that the other traffic can get service. Adding policing to that priority queue was ingenious because it keeps that queue from starving out the rest of your network. With that, let's get going with the implementation of both class-based weighted fair queuing and then transitioning into low latency queuing on a live Cisco router. Now you might be looking at that topology and going, wow, look at that topology. But really, doing it on a single router is just as good as doing it into an enterprise size environment. The reason I'm using just a single router is because I have a live internet connection connected up to that router, so we'll be able to see some live traffic going through and how queuing ends up treating it. So the first thing I want to show you is I want to get you familiarized with the environment that's sitting on our Cisco router. I'm going to do a show class map. And what I've done is I've created 3 different class maps. I created a class map with a match all of web, that's what I named it, match protocol of HTTP. I have a match all of FTP with matching that protocol. And I went ahead and did a match all on BitTorrent because I thought, hey, I can simulate that traffic easy enough. And I'm matching the protocol of BitTorrent. I installed that PDLM on my router for NBAR. I also have, of course, the class default, which catches everything else. Now, I went ahead and set up a policy map. I'll do a show policy map. And what I did was I created a policy map named marking. And for the class web, I set everything with IP precedence 3. FTP is 2. BitTorrent is 1, and then the default will end up marking with precedence of 0. Now I've left this running for a little while and walked over to my Macintosh and generated some traffic. And let me do a show policy map interface fast Ethernet 0, which is where I have this applied. You can see that the web has had 874 packets, about 150 or so kilobytes of data, and it's matched all of those and marked them with an IP precedence of 3. And as I scroll through this list, you can see FTP, there's my BitTorrent, and I have some traffic going through that. And of course, the largest is the class default, which is all sorts of other traffic happening on this network, and I'm setting those with an IP precedence of 0. Now, as of right now, let me do a show run here. I have these. Let me get to my interface here. I have these applied to the interface fast Ethernet 0. Now this is actually the inside interface of my internet connection. You can see that I have interface Ethernet 0. This is the one connected to the service provider out there, getting its address from DHCP. And what I've done is I've applied the service policy on the input, named it marking. So as things are coming into this router from my internal network, it's catching them and marking them. Now, the difference of this in a real life scenario would we would have routers all over our environment, all over this little screen right here, that are marking traffic and all eventually coming down to this consolidation point, the internet connection. So in this case, I'm just setting it on the fast Ethernet 0, but we would have traffic coming from all sorts of locations all around the network, all marked with their specific IP precedence values, like I did with that policy map. So now what I'm going to do, go ahead and clear all this off the screen, is I'm going to create class-based weighted fair queuing and provision sections of bandwidth for each of those traffic types. The first thing that I'm going to do is get into global configuration mode, and I'm going to create class maps that match the different precedence levels I have set on my network. So I'll create class map, and I'll say, I'll just name it P1 to match IP precedence 1. I'll say match, followed by IP precedence. Oh, and by the way, just so you don't get confused, I could type match precedence, or match DSCP, or I could type in match IP precedence or DSCP, because both of them mean the same thing. Cisco, I guess, just created redundant commands for that. And I'll say match IP precedence 1. I'll go ahead and create a class map P0, match IP precedence 0. All I'm doing is I'm taking these and putting them into their own class maps so that I can match them. Now, since I have a single router, could I have done this a lot easier? Yes, I could have. I could have matched the different traffic types using NBAR or whatever method coming into my my router, and then shape them into class-based weighted fair queuing from there. But I want to do this just like we would do it in a production environment, just like we would do it on a real network. This router is going to be getting traffic from all kinds of sources all around the network. We need to match them by their previously marked IP precedence values or DSCP values, depending on what you're using, that are being marked all around the different areas of our network. So now I have my class maps created. I'm going to create a policy map, and this is where the action comes in. Policy map of shape. Now from there, I'm going to have quite a few options. And you can see right now all I have to do is go under the class mode. Let's go under, I'll do IP precedence 2. I'm going to start there, or class P2. So for class 2, I want to go ahead and say that I want to assign a certain amount of bandwidth. This is how we configure class-based weighted fair queuing. I'm going to say bandwidth followed by, and I can type in either a certain kilobyte amount, kilobits per second, kilobits per second that I can type in there, or I can use a percentage of the interface bandwidth. Now, here's a rule of thumb. The Cisco router, by default, keeps you from using any more than 75% of the interface bandwidth. So if you start chomping up the percent by saying bandwidth percent, and let's say I wanted to use 10% of the interface bandwidth, well, what's going to happen is as you approach the limit of what you've configured with a bandwidth statement, once you hit 75% of that bandwidth, it will actually say, sorry, can't apply this policy map to the interface. So you got to be careful with that. I can go ahead, percent is nice because it doesn't matter what interface you apply it to, it will calculate the correct percentage. Remaining percent is one of the most confusing ones that's out there. The reason I say that is because let's say you use 50% of your interface bandwidth for this traffic. Well, you could do another class map and configure it to say, I want to use 20% of the remaining percent that's left over, which would be 25% of the 75%. My word, just saying this gets jumbled in my head. I hardly ever use the remaining percent. I just use the percent, or I get to specify exactly the kilobits per second that I allow. So if I type in bandwidth followed by 100, what that does is that ensures no matter what, this class of IP precedence 2 will get 100 kilobits per second of bandwidth. So now be careful with this. I want to make sure you guys get this. Does that mean that they are limited to 100 kilobits per second of bandwidth? Not at all. I can type in their bandwidth 100 and it guarantees they will at least have 100 kilobits per second of bandwidth, but if there's no congestion, they're going to get more. Remember what I said way back in the first nugget, and I said queuing. It only happens when there's congestion. Congestion management only happens if there's congestion. So it's not saying they'll only get 100 kilobits per second. That's what the job of policing does. This just guarantees that they'll get at least 100 kilobits per second. All right, so that's precedence 2. Let's go ahead and say class P1. And for that one, I'll say bandwidth of 50. If I have congestion, they will get at least 50 kilobits per second. And then for class, I'll do class P0. And for this one, let's go ahead and say bandwidth as the default queue that I tagged with precedence of 0. I'll say bandwidth, and we'll put the lowest amount. They're guaranteed 8 kilobits per second of bandwidth for that default queue. So what I've done at this point, and I still need to apply it, so let me get out of this and get into interface Ethernet 0. That is it's a cable modem connection out to the internet cloud out there. I'm going to say service policy output followed by the name of that policy, and it was, I believe, shape, if I remember correctly. Yep, policy map shape. So at this point, I have deployed class-based weighted fair queuing. I've divided it up into the different classes and given them a certain amount of bandwidth, and I can do a show service policy, show policy map. and I'll do interface Ethernet 0. And what I see here is I have the different priorities or different precedents that are coming through. And what I see right here is, here's precedence 1, and what I can see is exactly what's in the output queue at any given point in time. Now, I don't have enough traffic to really generate and overwhelm this going on right now, but you can actually see how many packets it's matching, how many bytes are going through of what's happening on that interface. That's all there really is to configuring class-based weighted fair queuing. So you notice that I went through here and divided up the different classes. I have IP precedence 0, precedence 1, and precedence 2, but I didn't do anything for precedence 3. Let me go ahead and do a show class map on here one more time. Precedence 3 matched everything with precedence 3, and let me look at my previous classifications, or actually let me do the show policy map and find out that we have web traffic. HTTP is being tagged with precedence 3. I'm going to deploy low latency queuing. I'm going to convert our existing configuration to low latency queuing because I haven't done anything with the precedence 3 packets. But I'm going to convert it to low latency queuing in a negative sense. Check this out. I'm going to get into global configuration mode, and I'm going to go into policy map shape. That's this policy map up here where I started dividing up the bandwidth. Using the bandwidth command essentially says I am setting up class-based weighted fair queuing. What is low latency queuing? Well, it's class-based weighted fair queuing plus a priority queue, that lawnmower queue that I can go ahead and add onto there. So I'm going to go under policy map shape and type in class P3. That's the one that I defined for the IP precedence 3 packets. And I'm going to use a different command. I've been using the bandwidth command so far, but now I'm going to use the priority command. You see this? Strict scheduling priority for this class. The reason it says strict is for twofold. Number one is it gets instant priority when it's coming in, but the second reason is because it's strict in the sense that it will never let it exceed the amount of bandwidth, either in kilobits per second or the percentage that I define right here. So I'm going to deploy low latency queuing, but in a negative sense. I'm going to allocate 8 kilobits per second for HTTP or web traffic. So what's that mean? What's it going to do? Well, what's going to happen, I'm going to reach over to my Macintosh over here and refresh the page. What it's going to do, oh wow, I can see that took effect. It's going to give web traffic 8 kilobits per second of priority bandwidth, meaning that, hey, that's going to go first before everything else, but what happens once it reaches 8 kilobits per second? It gets cut off. You got it. The priority queuing uses strict policing, so it's going to cut off that traffic to make sure it never gets more. And I went ahead and went to our local newspaper, the webpage on my Macintosh to my right-hand side, and it hasn't even loaded yet. It's still loading some of the pictures on the screen. I'm going to do a show, let me get my mouse out of there, show policy map, Ethernet or interface Ethernet 0, that's the one connected to the cloud. We have policy map shape, class map, priority 2, priority 1, there we go. Priority 3, this is the one. The output queue, the bandwidth is 8 kilobits per second. Look at this. Packets matched and bytes matched. It said it matched 229 packets totaling about 15 kilobytes. And look what happened is it dropped 43 of those packets because they exceeded what I set is my priority queue. So those are considered the offending traffic. Now you might be looking at this. Remember that I had this deployed long before I applied that policy. So the number of packets that it matched won't match up yet because I haven't had enough traffic after I applied this policy. But by doing that, I have given it priority bandwidth, but I have kept it from starving out the other packets in a huge way. So that's how we can combine the priority queuing with policing to make sure that it doesn't overwhelm the rest of our network. The last topic I want to discuss is something called congestion avoidance mechanisms. And there's only one of them really out there, is weighted random early detection. It's Cisco's spin on the industry standard random early detection, and here's the concept. And first off, let me read this bullet to you. It says, weighted random early detection avoids the problem known as TCP synchronization. Let's talk about what that problem is and how it happens. We have a huge speed mismatch right here. 100 megabit per second LAN connected to a T1 line. Now, if this computer represents 1,000 clients or 100 clients, what happens is these clients are going to try and send and receive as much as they can as fast as their network card will let them go. That's just how the clients work. Now, this T1 line's 1.5 meg versus the 100 megs that I'm getting over on the LAN side. So you have all of these clients coming through, and that will end up being the bottleneck. Now, here's the problem. By default, your Cisco router uses a system known as tail drop to drop packets. What that means is as the queues fill up, maybe you're using low latency queuing, maybe you're using class-based weighted for queuing, whatever method you're using, you might even be using FIFO. As the queues fill and the memory runs out, the router's just going to start dropping whatever packets come in after that. Now take that concept and apply it to what we know about TCP windowing. TCP has a unique system of windowing that allows it to increase window sizes as it feels the connection is more reliable. So instead of just sending one packet at a time and getting an acknowledgement, it'll start increasing up and saying, well, I'm going to try sending 2 packets at a time. How about 4 packets at a time? How about 8 packets at a time? Truth be told, Windows will allow it to keep increasing nearly to a limitless amount before it will end up getting all its packets dropped. So eventually, let's say all these clients have increased their window sizes to 16 packets that it sends per window, and it expects one acknowledgement to group all those 16 packets, and we hit congestion on this router. What happens? Well, all of the packets coming in get tail dropped until this has a chance to catch up. Now, I drew a little graph down here because I want you to see what happens over time. What will happen is the first client that this happens to will, well, let me start down here. We'll start off with a packet size of 1 and go up and up and starting using more bandwidth, larger window size, larger, reach the top, and wham, we drop. What will happen is when the client suddenly realizes the connection is no longer reliable, it decreases its window size back down in a huge way. So we might drop back down to, half that size, or maybe down to a quarter of that size on our window size. Then as it gets more reliable, it'll go back up, wham, drop back down again. So you have this bandwidth, and what happens, the reason it's called TCP synchronization, let me switch colors on my pen here, is eventually all the clients that are on your network will start following the same pattern. Imagine this pattern happening for all 100 or 1,000 clients that are behind you on the local area network connection, because all of them will start building up their window size. It's kind of like, I kind of think of it as, a quiet room, and one person starts talking, then another person, and then suddenly it's, everybody's talking, and then somebody else, quiet. That's the router. Quiet down. Everybody gets dropped and drops back down. Now here's the problem. This is our bandwidth level right here. Maybe this is our T1 line. Once we reach the capacity at T1, everybody drops. What about all this space sitting in here in the middle? What about this little gap that's always happening each time we have this dropping occurring? That little gap is wasted bandwidth. That's known as what's called TCP synchronization, also known as global synchronization, because everybody starts following the same pattern. That's where weighted random early detection comes in. Weighted random early detection says when I start detecting congestion, before I reach this limit, I'm going to start picking conversations and dropping packets. Now, with the industry standard known as RED, or random early detection, it just picked anybody. It said, all right, who's the unlucky victim today? You. And it starts dropping packets. So what happens is, let's say this green fellow right here, that one gets dropped off early. So it drops back down, but the rest of the network can kind of maintain their level up here around the T1, and it doesn't overwhelm itself. With weighted random early detection, which is what Cisco uses, or WRED, it allows you to specify what precedence levels or DSCP levels you want to start dropping first. The router can get selective and say, all right, who's going to be the unlucky victim? Let's look at IP precedence 0, wham, and start dropping those. So meanwhile, the higher precedences can continue on their conversation. It kind of works like this. Let me draw out a little bowl the best I can here. Think of it as like a beaker, like you used to have in your science classes. Each precedence level, I'll say this is IP precedence 0. Each precedence level will have something known as a minimum packet threshold and a maximum packet threshold. As long as you stay below the minimum on the amount of traffic that you're sending in, we have traffic kind of filling up this beaker right here, you're okay. Nothing's going to be dropped. But as you go past this minimum, the router's going to start picking off random packets. Let me color all this in. It'll start picking off random packets and saying, okay, this one's going to get dropped, this one's going to get dropped, hoping that the TCP conversations will start slowing back down and those window sizes for a few of the people will decrease, allowing the mini conversations to keep going. It's kind of like, I don't know if you've ever seen Star Trek Episode 3. I show my geekdom right here. We have Spock, who dies in Episode 3. And he says, I must sacrifice myself because what's the word? He says, the good of the many outweighs the good of the one. That's what weighted random early detection does. It follows Spock's logic. It says the good of the many outweighs the good of the one, so I'm going to sacrifice that one. And as you keep going further up on this beaker, it's going to start dropping more and more conversations until you reach the maximum level, and as soon as you hit the top here, it drops everybody. So the nice thing about weighted random early detection that's differentiating it from red is with weighted random early detections, you get to specify the minimum and the maximum level for each IP precedence level, all the way up from 0 through 7, or each DSCP level, depending on what values you're using in your calculations. You can say, I want to start dropping precedence 0 earlier by defining a lower minimum threshold. That's the concept of weighted random early detection. To enable random early detection or weighted random early detection on your router, the nice thing about it is it's simple. It's all about the concepts in Cisco. All you need to do is you need to get into your router, and I'll do a show policy map just so I can see my different policies maps, and I'm going to go under the shape one. Marking, marking does its marking, shape does the actual traffic shaping. So I'm going to get in there and do policy map, shape, and I'm going to type in class. Let's go ahead and start with priority 0, class P0. It's one command right here, random detect. Now, if you just type random detect and hit enter, it has a nice default policy that will apply, and it will most of the time do just fine for you. If you want to get in there and start tweaking your policy, I can say, I want to use random detect. It does IP precedence by default, but you can switch it over to DSCP if you'd like. I'll say random detect precedence. I could type here precedence, and I'll say for 0, which is what's going to be coming into this class, I want to set the minimum threshold, and this is all the tweaking I told you. Minimum threshold is once I have, we'll say, 20 packets in queue, the maximum threshold will be 100 packets in queue. And it says random detect on this class is required to issue this command. So I need to first off type in random detect, then I can type that command. There we go. And that sets the minimum threshold and maximum threshold for that IP precedence. Now let's go under class P1. And I'll type in random detect, turn that on. And for this one, I'll say for the precedence 1, I want to increase the minimum threshold and the maximum threshold so that this one will get dropped later on in the whole queuing process. I want it to try and drop the zeros, make sure see if that'll clear up some of the congestion. Then if that fails and my queues are still filling up, I'm going to start dropping precedence 1. And I can continue on up the list, turning on the random detect feature for each of the precedents and increasing it on how much that beaker, that queue, will end up holding for each of the precedence levels. That allows me as the administrator complete flexibility with how my traffic ends up getting dropped when there is congestion. That's why they call this a congestion avoidance mechanism, because you want to try and avoid this sort of symptom from happening in the first place. Phew, good stuff. Let's talk about the main points that we covered as we went through the quality of service in the queuing world and in the congestion avoidance mechanisms. We first off started talking about those legacy queuing methods, and I hope those analogies will stick in your head and help you remember each one of those methods. The FIFO, the line, the priority queuing as the lawnmowers, the donuts as custom queuing, and finally the meeting table as the weighted fair queuing. Those are really the building blocks that we use when we get into the modern queuing methods. All all of the modern queuing methods have to be implemented using the MQC standard. Cisco designed it that way, so you are unable to implement things like low latency queuing in the legacy CLI method. Finally, after we implemented those, we got into managing congestion using weighted random early detection. That's almost a misnomer. I almost want to say avoiding congestion using weighted random early detection, dropping packets early so that we can avoid having to get into all of the management methods by keeping that congestion from building up in the first place. I hope this nugget has been informative for you, and I'd like to thank you for viewing.